Hey guys, welcome back for part two of this three-part series that we put together for you. Dr. Hall, myself, and Dr. Vestal. You've already heard from Dr. Hall, and he kind of set the stage for this, and you'll hear from Dr. Vestal, and I get to kind of bat in the two-hole here and bring the eyes into play. So what we're trying to do is just introduce this idea of coronal plane movement or laterality as we move out through the brain. And Dr. Hall did a great job in setting the stage and kind of putting all the pieces together for neurodevelopment and why a lot of this is important cognitively and things like that. I'm going to try to bring the eyes into play here. And this is, the eyes are a complex subject, as anybody who's been doing functional neurology for a while knows. There's always something different. There's these little things that we can nitpick and pick out of how we're looking at eye movements and vision and visual processing and all those kind of things. We're not going to get real deep into the nitty gritty here today, but what I really want to introduce is kind of this difference between horizontal eye movements and vertical eye movements, convergence, some of the basics, and talk really about the horizontal eye movements and why they're a big piece as far as getting higher centers involved in the brain and getting into brain health in general, right? So if we just kind of look to start this off, the eyes are an important part, and we'll cover, some different slides here about how important and why they're important. But just to introduce this thought process of lateral or horizontal eye movements versus vertical eye movements, if we look at areas of the brain that are involved, right? So we know that if we are more in flexion, as Dr. Hall went over, and you guys have covered, I'm sure, in other modules and other things. If we're more in flexion, or flexors are tighter muscles, then that's a sign of a weaker prefrontal cortex, right? If we're standing more upright and more in extension, that's a sign of a healthier brain or a healthier prefrontal cortex. In general, you don't walk around an old folks home and see everybody walking around with their chest up high and their arms back. You see them more in that flexion. Going back to even fetal development, babies born in flexion, protecting the organs and things of that nature, and more in that limbic brain, less in the prefrontal cortex or less in that frontal lobe. So that kind of brings up that idea of the more inflection, the more vertical or up and down, the less we are in that lateral brain, the less we're more into prefrontal and things like that. So think of it in general like this. Midline structures go with midline structures, and the more midline the structure, the more primitive the brain. As we develop, even the neural tube and telencephalon, diencephalon, all of that stuff, rhombencephalon, as it grows up and then grows out, and the newer higher centers are more lateral, they're more out. And if you look at that, looking at the eyes in that horizontal plane, that's really about neurodevelopment and as we kind of come up and develop in that way. So we'll kind of set the stage with that and then go into some specifics on why the eyes really are super important and why we look at them. As a chiropractor, I don't think, and I know we're multidisciplinary here, but as a chiropractor, I think it would behoove us to look at the eyes and the spine, especially because of that relationship and how closely tied they are together. But then we'll talk a little bit about how much brain activation really comes from vision, or even less than vision. I want to start to think about this as not just vision, but how well the eyes move and how they're moving in different ways, because the movement, movement is life. Movement is also a big key to how we activate our brain and how we drive some of those neural networks. That's where a lot of that afferent input comes into play, right? We get our feeling and our sensory through our receptors. Movement is twofold. One, it's how we respond to our environment, but it's also another loop back in of how we feed our brain in a different way, right? So the eye movements, the body movements, all of those tie into brain activation, as well as brain smoothness, brain coordination, all of those things that we'll kind of touch on. So the eyes are a big part of what we do. I get some creepy looks sometimes. I catch myself looking at people's eyes when I'm people watching. You'll find yourself doing this too. You'll start to see all sorts of head tilts, and then eyes being with or without each other on the head tilt. And then different, ESO and exophorias and tropias that we'll get into as we talk through some of this stuff. But as we progress through this, the eyes are a big part of where we go. And the eyes are tied into a whole bunch of stuff. When we teach in more of a group environment, when we're actually live with people, I always ask the question, why do we have a spine? Like, what's your spine's job? And I almost inevitably get, they're all right answers, but almost always it's first about protection of the spinal cord. And that's absolutely right. That's a part of what your spine does. But if that's what the spine's job was, just like the other answer that I get is to keep us upright or allow us to walk upright, if that's what the spine's jobs were, it's not that those aren't part of it, but you wouldn't have all those little movable segments in there. If the job of the spine was simply protection, you wouldn't have it be movable because that makes it more vulnerable. If it was simply for us to be upright and allow us to move through space in 2 feet or bipedal, if that was simply it, again, you wouldn't have all of those little movable segments. You might have some movement at the top and the bottom and maybe in the middle to allow for locomotion, but it wouldn't have all those little movable segments. And the reason that we're finding is you have all those little movable segments because it's there to keep your eyes on the horizon no matter what position the rest of your body is in. So, Dr. Hall is often quoted as saying everything below the clavicles is a reflex. And even in the spine, it is as well. They're starting to, with research, tie the eyes into a lot of different disorders, or dysfunction in the eyes into a lot of different disorders. Scoliosis here being one of them. And this is a fairly old article, 2001, that they started to introduce this idea that the reason you get these curves and even rotations in the spine is as a result of some dysfunction in the way that the eyes move. If the eyes are, if you have a bit of a head tilt and the eyes have an ocular tilt reaction, you're going to have the spine trying to twist you out of that to really get you into these different positions to put both eyes on a target. Because your eyes are super important for a lot of things, right? They're your most important conscious daytime sense. They're what allow you to see friend, they allow you to see foe, they allow you to see food, they allow you to see shelter. So we rely on these for a lot of different things. We rely on them to survive, essentially. Just about everything that we do as a species, whether it's procreation, whether it's eating, whether it's staying safe, the eyes make up a big part of how we determine where and what and who and how. So it's a super important part of our nervous system. It's a super important part of how we take in the world. So we devote a lot of energy and a lot of activation to that. And as a result, it shows up when they're dysfunctional, it shows up in a lot of different conditions. So like I said, scoliosis being one of those. Whiplash. Again, I don't think as a chiro, we can do our job as well as we could if we aren't paying attention to the eyes. The eyes and the spine are connected from birth. The same embryological tissue, or the same somites, if you remember that word, that make up the muscles that move the spine, like multifidi and control postural things, also make up the muscles that move the eyes, the intrinsic muscles of the eyes. So the medial rectus, lateral rectus, superior oblique, they come from the same embryological or baby tissue as the multifidi and interspinalis muscles. So they're linked from birth. They grow together, they develop together. One thing I love to have people do just to show this relationship is to put your fingers on your suboccipital muscles. And then without moving your head, move your eyes back and forth as fast as you can. And you'll feel those little muscles firing up. So the relationship between the main proprioceptive muscles in your neck and your eyes, they're completely locked together. So we can't really ignore one or not pay attention to one and not pay attention to the other. So even for the optometrists that are out there watching this, understanding that relationship between posture and the eyes too, as well as the little musculature. So when we have a whiplash injury, like a concussion or a car accident, or any other way that you're going to get whiplash, looking at the eyes and the neck together is hugely important to get a really well-rounded understanding of what's going on. Obviously, vision in the eyes. There's a lot of vision, whether it's double vision, whether it's blurry vision or things like that, all tie into how the eyes move together, right? If I have a head tilt like this, and if I have a head tilt here, my eyes should correct to kind of keep me on the horizon, right? That's a normal ocular tilt reaction, is if I tilt to my right, I should have my left eye drop down a little bit and my right eye come up a little bit to keep my eyes on the horizon. But what about in those instances where it actually accentuates that? I might end up with things like dizziness. I might end up with all sorts of issues related to things like double vision or nausea, or insert symptom here that's associated with aberrant visual information coming in. And obviously vision and double vision and vestibular issues all related to that. If we have some, frontal lobe deficits, we'll talk a little bit about how the eyes move in different directions. Your frontal lobe does the fast eye movements, or what are known as saccadic eye movements. And if we have an issue with our frontal lobe, again, you might end up with more flexion. You're also going to see an issue in those saccadic movements. And we'll talk about a condition here in a minute known as convergence insufficiency that really ties some of that in for like reading disorders and dyslexia as well. So obviously vision, not hard to make that connection between vision and the eyes, right? It's kind of what they do. Posture in the eyes, going back to that whiplash conversation, if we're struggling for convergence, or we're really struggling to get our eyes up and out, we're going to end up more in flexion. If our eyes tend to come down and in easier, which is what a lot of us do right now, right? We're taking away from that ability to get up and out. And that's really why, I think what the catalyst for why we put this together, Dr. Hall, myself, and Dr. Vestal, was to talk about the importance of getting up into that coronal plane. Because right now, more than ever, our society is kind of getting pulled down into that flexion or that sagittal plane more, doing things more vertical, ending up with more issues with addiction and depression and anxiety. If you look at the numbers, especially through the pandemic, depression numbers, anxiety numbers went through the roof. Suicide numbers tripled at different points of isolation during the pandemic. So this idea of getting into that coronal plane, and posture really being a big part of that, is how we measure health of the brain, or function of the brain, or tone of the brain. One of my favorite quotes, and no matter how hard I look, I can't find out who actually said it, but the quote is, "Posture is the shadow of the brain." And if we're in that flexion posture, that's kind of a bad shadow. That's weakness, or a decrease in central integrated state in that brain, or a decrease in the overall hum of the brain, or the level of activation. So our posture, if our brain's weak, our posture is going to be bad, and our eyes are going to struggle. Something that we often see with kids with learning disabilities, or something you're seeing a lot more often in our office anyway, is these really, really little kids coming in with their glasses, the colored ones, like the orange or red, I think are probably the most common that I see. But you've got younger and younger kids needing glasses. And those same kids that need the glasses also have really bad posture. And again, kind of tying on that midline structures, go with midline structures, they're also the ones that develop speech late, or don't swallow solid foods late, they don't develop the ability to swallow solid foods until late. Those midline structures go together. And when you see a breakdown posturally, you're going to start to notice that they had those issues also, or that when you start to ask questions of mom and things like that, you'll notice some of those questions. So posture really does tell us a ton about where we're at from a brain health perspective, and the visual system ties into that big time too. Vision will lead posture, and posture will break down your visual system, or your eye movements, your what we refer to as oculometrics as well. And then headaches, obviously, this is another one I think most of us kind of get and know, but a lot of research out there on headaches and different versions of head pain, and how well the eyes move together and how well they coordinate, right? Because that's what this is really about. It's about coordination. And as we talk about this, it's having coordination in that coronal plane, having movement into that coronal plane really brings about a lot of different things in the brain, and why it's important to get out there. Vertical eye movements, I don't think most people need help with doing more vertical eye movements. Anybody who has one of these does plenty of vertical eye movements. Most of the stuff that we have is that vertical scrolling kind of thing that people get stuck into for long periods of the day. So we have enough of that activation. Getting into that coronal plane, I think, is where we need to venture into a little bit more. So again, eyes kind of tie into a lot of different things, a lot of different conditions, a lot of different aspects of brain health, right? Something else that as we start to see, I thought this was an interesting report that by 2050, we're going to have 4.8 billion people being nearsighted or needing glasses. So most babies are born myopic, right? We understand that the medial rectus is kind of that dominant eye muscle when babies are born. And then it isn't until we roll over and we start to do some tummy time, the head comes up, the eyes come up and start to be able to play in that horizontal plane, right? That's a sign again, extensor tone, less flexor dominant, and more extensor tone allows us to come up and do that. That's a healthier brain. We're starting to, with extensors, drive into the cerebellum, which then drives our prefrontal cortex, which is ultimately the part of the brain that makes us happy and healthy, right? So this should alarm us a little bit that we're kind of reverting back to that. That most people, almost 50% of the world's population, is expected to be nearsighted. Some other interesting things that are going to happen by 2050, and you start to see some parallels in this, right? In overall weakness or decrease in tone of the brain or brain health or central integrated state, and some of these conditions that they're predicting. So by 2050, Alzheimer's is also supposed to be rampant and crippling our economy. By 2050, they estimate that 1 in 2 kids is going to be on the spectrum or be diagnosed with autism. And now also looking at myopia or nearsightedness. I think all of these things tie together and they paint a picture that's not real great about brain health and kind of where we're headed. You know, there's some books out there, there's a school of thought that we don't need glasses, that glasses are kind of a weakness that when we put them on, we continue to go down. It's essentially, you know, some people would compare it to putting a brace on something. If you put a brace on something, it's not strengthening the issue. It might give you some stability, but it doesn't actually strengthen what it is you're trying to make stronger. There's a thought process there around that with glasses, that instead of putting glasses on people real early, then maybe we should do some eye exercises or work on posture and work on some of that. And I think in the realm of functional neurology, I know we get a lot of that in our office right now. And in the realm of functional neurology, I think that fits really well into our wheelhouse. You know, if you don't want to do a lot of the eye exercises to prevent these kids from getting on glasses, maybe you do the postural stuff and you have someone from NORA or the Neuro-Optometrist Rehabilitation Association do the eye part. You know, we share a lot of patients in Atlanta with Dr. Cook. And, you know, you have somebody that does that really specialized part, then you can focus in on the postural things. You know, for me as a chiropractor, I can focus in on the postural things. Same thing for the optometrists that are listening. If you want to focus more in on the eyes, having somebody pay attention to the neck and the spine and the muscles that are there are hugely important to really coordinating that care. And that's what I love about this group with iApner, is that we have so many different types of professionals. We need to start to use each other more and be able to lean on each other, because, you know, what someone else's specialty is isn't necessarily my specialty. But there's a lot of ways to brain health, and a lot of these things come together. You know, even again, looking at this, nearsightedness, you know, being on the spectrum with autism and Alzheimer's, those are 3 very different populations of people that a lot of times wouldn't be thought of or put together in the same group. But I think when you start to look at the brain and you start to look at what we're talking about, it really comes together more. And I think with our advanced understanding, as we start to understand and unlock the brain a little bit more, it opens some doors for us to understanding this better, right? So just something that I thought was an interesting stat out of the Journal of Ophthalmology, and something that ties really into this kind of eyes and spine and brain health as we look through this stuff. So this is another condition. If you guys have heard me speak before, I tend to talk about this at least once because I think it's hugely important. Convergence insufficiency. So convergence is one of the basic eye movements that we have. It's one of the first things that we have to do. If we're going to look at anything, we have to first have both of our eyes looking ahead, but coordinating in to look at that target together. If one of them comes in a little sooner or a little further than the other one, that's going to be a breakdown in convergence. So when we're doing this and we're looking at all of these eye movements, and again, I'm not going to go super in depth into how to test and all of that kind of stuff. We actually did a neuro exam module that's part of this conference if you want to check into that more. But you know, when we look at a breakdown in that convergence, it can mean a lot of things in a lot of ways. When you look at the literature, what first cued me into this was they actually believe a lot of kids are getting diagnosed dyslexic, and the reality is it's probably more of a convergence insufficiency. So, and where we go with that is dyslexia, obviously learning disability, it's a problem. I'm not saying dyslexia doesn't exist, but in a lot of cases, it could be an issue more with how the eyes work together or how they come and work in coordination. So when I have a breakdown in my eye's ability to focus on one target together, that can be the start of the problem, right? So what we're noticing with kids is, and we've, you know, for a few years now been working with this and still seeing quite a bit of it and even more of it. Again, as we see that posture breakdown, as we see the kind of frontal lobes not getting driven as well. And I'll try not to get on my soapbox about technology and how that contributes to all of that, but we're going to have to touch on that a little bit. But with this convergence, if you have a breakdown in the ability of the eyes first to come together to look at a word, you read words as pictures. And if they don't see, if both eyes don't see the same picture, you're going to get words flipped, you're going to get letters flipped, you're going to struggle to really read. And if we know that a breakdown in your ability to converge also then is going to struggle to jump from one word to the next, right? And so if you're already picking up a bad first picture and then you can't jump to the next word very accurately, you're going to pick up two different pictures and you're going to read really slow, right? You're going to have eye strain, you're going to have headaches, you're going to have blurred vision, double vision, trouble concentrating, a really short attention span, especially on reading. You're going to lose your place. You're going to get to the end of a paragraph and forget what you read. These are the kids that kind of squint and rub their eyes a lot when they're reading, or their eyes will tear up, things like that. These are also the kids that when they're reading, you'll notice they're struggling with their eyes, and you'll see their tongue is also out, kind of like this while they're reading, or they move their tongue into their cheek. And that's trying to help. Again, those midline structures go with midline structures. So they try to activate the tongue, that cranial nerve 12, to help move the eyes. And so you'll see a lot of these things, like words appear to move, jump, swim, or float. This is the kid that gets vertigo or motion sick when driving in the car too. They really struggle with seeing things and the coordination of the eyes. And again, there's some literature out there that says dyslexia is getting confused with this inability to converge on a target. So we see a lot of things, right? You could diagnose, if a kid came into a lot of doctors' offices that maybe didn't know what we know, they might get diagnosed with ADD, right? Short attention span, trouble reading, inability to concentrate, slap that label on them and keep them moving, right? Our understanding, you know, as being part of this group and understanding more about the brain and you know, you guys out there, how we can help these kids get a little bit different treatment or a little bit better understanding. We've had kids that they wanted to hold back a year in school because their inability to read and get labeled dyslexic. And just in working on some convergence, some postural activation, we were able to get them to, you know, pass their tests and move right along with their class, and then not get put in that special classroom or get that label put on them of dyslexia. So this is something that we can really start to focus on, because you have to be able to converge on a target to be able to move horizontally as you go. So we need that coordination in those two systems. And this is a big thing that starts to show up, right? So to go a little further with this, this is one of my favorites that shows kind of how the two sides of the brain play back and forth. Again, it's a horizontal movement with the eyes, the way that we read, but it also shows some connectivity between the brain. I know a lot of you guys that are watching this have probably seen this stuff before, so I won't sit on this very long, but the idea is you read it top to bottom, left to right, like you would read a normal piece of paper, and you read the word first as you go horizontally each down the line. Then you switch and you come back and you read the color of the ink. Now the first two lines match up. But after that, it starts to be alternating or different, right? So it's what's called non-congruent color matching. So the first ones, the red, blue, orange, purple, orange, blue, green, red, are all congruent. The word says the same thing as the color. After that, it's not congruent. So the idea is, or the thought is, that you read the words with the left side of your brain and you read the color of the ink more with the right side. So this shows, or is known as, a frontal switching task, or your ability to switch from one side of the brain to the other, looking at kind of those callosal fibers, but also how you integrate or coordinate the two halves of the brain and how they're working. There's some research that's been going on now for a while in Japan. They're trying to actually measure your brain age with this test. And basically what they're saying is the faster you can get through this test, the younger your brain is. The longer it takes you, or the more that you struggle with this, the older your brain is. So they're trying to find a way to measure kind of if your chronological age, so to speak, matches your neurophysiological age. And if not, can there be some things that are done to help that? It brings in this idea of cognitive resilience or cognitive flexibility too. This is another big thing that you see with this task, is your brain's ability to be flexible. Can you jump from one task to another, or do you get really locked up in one pathway? And a young brain has the ability to switch and jump and do different tasks very smoothly and very quickly. The older our brain gets, the harder it is to kind of jump into another pathway, so to speak, or stop what we're doing and switch gears, so to speak. So it brings in this idea of flexibility, cognitive reserve, and some of the other things that they're really starting to try to use to both measure brain health and cognition, but also in building these programs out to improve brain health and cognition. So I know we've seen these before, but a really fun way to use this. You can put a metronome beat with this and start to work on balance and or timing and coordination with it. We often have people read this while they're doing a balance board or doing a balance platform, and you can really start to layer some things on top of doing even something simple like this. I like this one. This is what gives us a good understanding of reading in saccades, right? And if you read through this, again, coming back to that convergence and sufficiency, we first have to be able to converge on the target and read the word. And then you actually read as a saccade or as a fast eye movement. We don't pursue along the line. We jump from version to version, or from word to word to word, or picture to picture to picture. And your brain gets so good at reading and understanding pictures, as long as it's seeing the same picture, it doesn't even need all the letters to be there. It understands and it picks up very quickly what it is that you're doing and what you're reading. So that's how quickly our brain takes in that visual information when it's appropriate and processes that. And even more so, why it's so important that both eyes are looking at the same picture, because when they're not, and when you're looking at two different things, we tend to get really discombobulated and misunderstand what it is that we're doing. We start to flip words, letters, and that's why, again, if we notice we struggle to converge, we're also coming more into flexion. We're less in our ability to be horizontal in our eye movements, right? So it's going to decrease our ability to converge on a target. When we're in that flexion, weaker frontal lobe, right? Frontal lobe is what does fast eye movements or saccades. So we're starting to see how all of this stuff plays together, why that frontal lobe posture, or being upright, having that upright posture, extensors, bringing the eyes up and on the horizon and allowing us to scan, is so important for that higher centers or more lateral brain. When we get more into those vertical eye movements, we actually come more into flexion. It brings us more into sagittal plane and shuts some things down. I'm gonna belabor this point as we go, because that's how much the eyes really start to drive our posture. When we work with elderly patients with like Parkinson's or with Alzheimer's, they have that really bad camptocormic posture in their forward flexion. They're almost always kind of looking at the ground when they walk. And something we get in the habit of telling them is, you're going to go where your eyes are. So if your eyes are looking at the ground, you're probably not far from falling or getting there, getting closer to the ground. If your eyes are up on the horizon and able to scan, And even with the horizon, that's going to be healthier. You're looking where you're going. Your body's going to follow where that's going. So again, just like the baby, when they're doing tummy time, brings the eyes up and out and starts to break that myopic vision pattern or the dominance of the medial rectus by driving more of that horizontal gaze. The same thing happens in an older person. If they're here and they're flexed, that's going to be bad for their posture, their brain, and their balance. If their eyes are up and on the horizon, it goes a lot better. You know, another thing, we do a lot of balance exercises with people. We have something called a voodoo board. It's like an Indo board, if you've ever heard of those. It's basically a skateboard or a surfboard looking thing that sits on a little rock. It's like a little roll, essentially. I think Dr. Rest is going to talk about this stuff when he gets into his coronal plane movement for the body and for the head and neck. But it's a little roll that kind of goes side to side. And what you'll often see is people will stare at their feet the whole time they're doing it, and they struggle until I tell them to get their eyes up and focus on something on the horizon. And then it's almost like their brain just clicks and their balance becomes stable. And it's really eye-opening for a lot of people that, you know, well, I thought I had to watch my feet. Your feet aren't going anywhere on the board. And once the eyes come up on the horizon, it'll actually stabilize out the feet, right? Through those vestibular ocular reflexes. We've got some other like pelvo-ocular reflexes and some other things that stabilize you when the eyes are on the horizon. We do worse when we're looking down at our feet. So again, I'm going to kind of belabor that point as we go through this, because the idea really is getting the eyes up and on the horizon and then scanning the horizon is going to activate into that more lateral brain, getting you more into that coronal plane, which is really where we want to be for brain health, for lateral activation. So we've hit some of this stuff here already. How important are the eyes, or how important is vision? Sight is your most dominant daytime sense. Proprioception has more receptors, more activation. Obviously, it's a bigger input to the brain overall. But even with that, even with all the muscles and joints and everything like that, 40% of all the nerve fibers to your brain come from the retina. And what I mean by that is all of the information just from those little cells, the cones and the rods, all of that make up a huge input into the brain and how we process information. Every movement processes eye movements and vision and different parts of it. You know, we learned that the occipital cortex is where vision happens. But when you really jump in and you start flipping through Lee and Z, you see how much of the brain is actually devoted to moving the eyes and coordinating the eyes, processing vision, processing movement in your visual field versus static visual field versus putting the two of those together. There's a lot of understanding there that happens. 2/3 of all electrical activity in the brain is devoted to vision when the eyes are open. Dr. Shidlovsky actually showed me something that even when your eyes are closed, there's a huge amount of visual processing that's happening. Hopefully he doesn't bother me, or he's not bothered by me telling this story, but when we were at the Sports Vision Association meeting up in Utah, he had put some prisms on me. Well, before he put the prisms on me, he had me close my eyes, and then he snapped at different places in space. And you guys have done this test before. You snap, and then you have them kind of touch that space, right? And what you're looking for is how well they can auditorily process the environment and get to that. At least I thought that's what they were processing, was just the auditory part. So he had me do that, and I was pretty accurate. I was pretty good at hitting the different spots. Then he put a pair of prism lenses on me, and I don't know which ones they were, if they were inferior, superior, or where he was trying to drive or what he was doing. And I'm not even sure it matters much for the test. He put the prisms on me, had me keep my eyes closed, and then he snapped again. And I was like, not even in the right quadrant. So if he snapped up and to the right, I was touching like down and to the left. I mean, it was crazy how different it was. And I wasn't even consciously processing my vision. So you're processing your vision even when your eyes are closed. You're still picking up. I mean, think about it. You got these things, these eyelids are pretty thin, and it's pretty easy to see through, especially when there's light behind it, right? So we still are processing things, even though when the eyelids come down, we shut off that signal, or we at least shut off the processing of it in the occipital cortex. Brain tap is another great example of this. You never do the brain tap with your eyes open. you always have your eyes closed. And if you guys haven't done it, it's got these little goggles or this little shade that comes down in front of you and it flashes light, flashes blue light. It does what it needs to through the eyelids. And if you do it with your eyes open, that's when you can induce a seizure and really kind of mess yourself up. So you actually have to close the eyes, but it still processes that flashing light. There's some research now as far as breaking up neurofibrillary tangles or the amyloid, beta amyloid plaques associated with Alzheimer's. They think they can break those up with a gamma flash into the eyes, listening to gamma wave as well. So, but the eyes aren't open during that. They're closed as you introduce that pathway or introduce that. So it's our most important daytime sense, but we're actually using vision even with the eyes closed and processing our environment that way, kind of subconsciously or unconsciously, which I think is pretty cool. So again, vision, hugely important. We devote a lot of energy and brain space to that. This is just an example of that. I love this picture, not because we're going to go over all of this stuff and things, but this is just how we generate a saccadic eye movement. This is how many brain areas, if you look at all the lines and areas that are processing and doing different things, this is just for a memory saccade. So for you to be able to look at something you already knew was there or thought you knew where it was, keeping motivation, keeping attention on that. There's a lot of different things that play into this, right? So you process, I know we learn occipital cortex is where we do vision, but the reality is just about every lobe of the brain or every area of the brain has something to do with the eyes, right? Again, we're not, if we were going to do vision, you guys have seen Lean Z, right? It's huge, it's hugely thick. We could do a whole weekend module or a whole 4-day thing just hitting the top part of that. It's a hugely complex subject, but just to kind of highlight a little bit of it, of where all of this stuff, all of that energy and activation is devoted to in the brain. So every lobe of the brain plays with vision. Every lobe of the brain can affect your visual streams. It can affect your visual coordination, your eye movement coordination. So again, why it's kind of important to take a look at the different areas or different eye movements as we look. I always love this picture just kind of as a break, right? You know, you were doing your job, right? You were created here in the right way. So hopefully everybody can see horse kind of written along the horse, right? So our eyes will also kind of play with things too. And there's a lot of ways that we can confuse the eyes. We can play tricks on it. That's essentially what card tricks and magic are. Using your visual system against you in a way, using our ability to really fine tune and see things and pick up on things quickly and think we know where our attention is can actually be used against us in some ways too. And, you know, this kind of brings up, I always love using this one to introduce like Rorschach. If you guys remember ink blots from back in the day, they used to diagnose mental health and psychosis and things like that based on what you saw in the ink blot, right? If you didn't see a butterfly, then you had a serious mental health condition. So our eyes, big time playing into a lot of different aspects of things. And only perfection works, right? We need to be able to see clearly. Otherwise, like I said, with convergence insufficiency or with a problem focusing on things, you're going to devote a lot more energy to trying to make it happen. That's why people, you know, that do need glasses, they develop headaches or they develop things. You literally are running out of energy in the brain, and your brain's trying to tell you through a headache or through some sort of symptom that something's wrong. So we need to have that perfect vision. This is a great example of when it starts to break down. And so if you watch this is a VNG. And for this test here, he's doing a smooth pursuit in a horizontal plane. And so the dot, for those of you guys that aren't familiar with this, the dot is just going to smoothly move back and forth across the screen like that. And just tell me how well you think he does that. And that is not the video skipping. So you see big jumps in his trying to pursue that. He's like a catch-up saccade, or he's trying to keep up with the target. He's really just very lack of coordination. And we see a lot of things when we see breakdowns in eye movements like this with this case in general, or in particular, he had some mental health issues that went along with it. obviously he's going to have trouble reading or coordinating eye movements in other ways, right? So his grades were really suffering in school. So mental health, cognition, all sorts of things. He was actually having some tics and movement disorders that went around with this as well. And as we start to clear those eye movements up, we saw a lot of those things drop away. So, you know, this is one where we worked really hard on the eye movements and balance in him, and we're able to make huge changes pretty quick. But when you see that imperfection, you start to notice that. And this was a concussion case, and he had been cleared to play, actually, even though his grades were suffering and his mood was a problem, but he wasn't having any dizziness or headaches anymore. He'd kind of dampened that symptom or those symptoms, but he was still having a lot of other things going on. And that's why I think it's important for us to understand how the eyes move together, because his neurologist said, can he look left? Can he look right? And he could. But what we do from that functional neurological perspective is understanding how well he does that. And when you see those breakdowns, you start to tie some of that dysfunction into some other conditions. And we can, once we clear up that dysfunction, we can help with a lot of those other dysfunctions that are going on, like the mental health and some of those things, right? So again, kind of bringing it back to how we developed the first time. When the baby starts to roll over, they're starting to develop more of those postural muscles. They're starting to develop more extension. That's why tummy time is hugely important. You know, I think it's funny, we pay attention to tummy time in babies, and then we ignore it as adults. I think we might even need to get some adults into some tummy time to start to activate their extensors a little bit more, because we spend a lot of time in flexion in our day, right? You might get up out of bed and go sit in your car in flexion, drive to the office, sit down in flexion at a chair on a computer, and you go home and you sit in flexion to watch TV, sit in flexion at the dinner table. We need to figure out a way to get adult tummy time in, right? Or at least some upward mobility. And coronal plane movement, I think, is where you go. You know, babies, tummy time is great because they can't get up and drive those large diameter afferents in. But the tummy time equivalent for adults is that coronal plane movement. So if you look at this little guy, he's got the tongue sticking out. He's really working on developing those eyes up and on the horizon, right? As he drives into those extensor muscles. It's the same thing when we start doing that coronal movement. You can't do coronal plane movement with your arms flexed. You have to shut those flexors down, activate that extension, which is essentially what you're doing with tummy time, right? So as we do this coronal plane movement, whether it's jumping jacks, whether it's on a voodoo board, or whether you're using your eyes in the horizontal plane more, those are hugely important to driving those lateral areas of the brain. And it's important that we get this adult tummy time in, or this, you know, post baby tummy time versions, or post baby coronal plane activation, because we do enough inflection, right? And I said I wasn't going to get on my soapbox a lot here, but the more flexion or even vertical eye movements that we do, the less brain activation we have. And these devices, they're not going anywhere, right? They're going to be here. So we're not getting rid of them. So I'm not saying technology is evil, throw out your cell phone. It's just not going to happen. People are going to be bombarded with these though. And the more they're bombarded with it, the more they need that coronal activation. One of the things they do with these, if you guys have ever read a book called Irresistible, there's a documentary on Netflix now about the internet and kind of what it does to our brains and how they develop apps and all that kind of stuff. They're done very specifically. The people who develop Apple iPhones or any of the ones, I'm not picking on Apple, they have neuropsychologists that are part of their team. So they're in their development of the apps and the technology, they actually are purposely kind of shutting your frontal lobe down. And they do it because they want to keep you addicted, so to speak, to that technology. And that's why it's not a mistake that Facebook and Instagram and all those things scroll vertical. Because when you have a backlit screen, you do a few things. One, the backlighting. The first place you perceive light in your brain or in your nervous system is one at the retina, but then that signal immediately goes to the mesencephalon. And what's important about that is we send light to the mesencephalon so that we can then activate the pupil to constrict against it. But dopamine's created there too. And if you keep firing into the mesencephalon and you keep firing off dopamine, dopamine eventually runs the show. If you guys remember the basal nucleus or basal ganglia, you've got the direct pathway and the indirect pathway. That's supposed to be initiated by the prefrontal cortex. But remember, you've got your D1, D2, D17, receptors on the striatum, the second place there where the cortex is supposed to feed, that's run by dopamine. So in the absence of brain activating those movement loops or frontal lobe activating those movement loops, dopamine will. The problem is when dopamine starts to initiate that loop, now you end up in kind of an addiction. And when dopamine initiates that loop, it shuts down through negative feedback, it shuts down the prefrontal cortex. So you get a hit of dopamine when you look at the screen, right? That blue light. And then you get a hit of dopamine when you vertically scroll. If you look at here, I'm gonna skip around on my slides a little bit. Horizontal eye movements are more frontopontine. So when you get into the lateral movement, you're driving pons and you're driving frontal lobe here through frontal eye fields. Vertical eye movements are more mesencephalic. So they're more going to drive into our vertical saccade centers are in the mesencephalon near the substantia nigra. So when we get into those vertical eye movements, we create more of a dopamine hit to go along with that backlit screen giving us that dopamine hit. And again, when we run on dopamine, we literally downregulate the prefrontal cortex. And the more we run on dopamine, dopamine being our reward neurotransmitter, the more we want to do or need to do those things. So it's no mistake that most people are addicted to technology at this point. And they're starting to recognize that more, even in mainstream, that you're addicted to, but it's done on purpose. They have teams of neuropsychologists that develop the apps, develop the programs. They know exactly how many clicks it'll take you to stay wanting to click. They know the right colors to use, the right sound patterns, and the right way to combine these things to get a quick dopamine hit to make you need that more or want that more. So that, and again, these aren't going away. So I'm not saying it's evil and we can throw out our cell phones. That's just simply not going to happen. But it's more important for us now more than ever, because of the existence of these things, to tell our patients and let them understand and develop programs for them to do more of this coronal plane movement. Because we need to activate the muscles here, we need to activate our extensors to get us up on the horizon, right? The vestibular system is that primitive part that the baby's using at first, until we start to drive into these little muscles here. Once we get these muscles firing, now we start to drive the spine, we start to come upright, walk around, and we can start to really drive our brain and coordinate different things. And that's when we really start to grow our higher centers. So it's important that, again, kind of coming back here, as we look at our lateral eye movements, it's important to work more in that coronal plane, more on the horizontal plane from a visual standpoint, than it is in this sagittal plane with flexion and vertical eye movements, because it allows us to drive into those higher centers better. And like I said, now more than ever, we need that. Because I almost don't like the comparison of text neck and things like that, because it talks about people's heads being down, but people have always read the paper in that position. They've always done those kind of movements. The biggest difference is that we don't move anymore. We don't get out and play anymore. We don't run and jump and climb on, monkey bars or the big thing like we used to as kids. One of the saddest things my brother ever said was he knew it was summertime because he didn't see any kids outside anymore. It used to, like during school, he would see them going to and from the bus, but then they'd be inside playing video games. And in the summer, these kids were just kind of locked inside, not doing anything. And that wasn't how we grew up. Like my mom had to come get us when the streetlights went on, because we weren't coming inside for anything. We wanted to be outside running and jumping and playing. So we just don't do that much anymore. We don't get our eyes up on the horizon scanning side to side in the larger field of vision. All of our fields of vision are about 32 inches or 62 inches, depending on the size of the TV you're watching or playing a video game on. So it's even more important that we are that message to our patients, to talk about getting the eyes up on the horizon, doing some vertical scanning or some horizontal scanning to really drive into those higher centers. And this pathway, working through that frontopontine versus mesencephalic and dopamine and almost nigrostriatal, to drive into some of those pathways. This kind of frontal pontine cerebellar is going to drive higher centers better to get that activation more where we need it and more into the lateral brain, right? As Dr. Hall laid out, as we develop, as the baby grows, as the eyes come up and onto the horizon, that's where vision starts to become our important sense. And then we can use vision to drive a lot of those areas of the brain. And as Dr. Vestal is going to do with you guys next, he's going to talk about how not only vision, but the rest of the body needs to move around this as well. And as you develop these programs where we have horizontal eye movements, what does that look like from a body perspective to match what that looks like so that we get a lot better brain health in there? Because movement is life, but sometimes better movement is better life, right? So if we understand the difference between sagittal movement, which we do a lot of, and the difference then into coronal plane movement or, horizontal plane, then it gets better movement, better life, better brain activity. So hopefully you guys enjoy this little this three-part talk that we put together. Dr. Vestal is going to give you some great tips on how to bring in some body movements along with what we're talking about with the eyes from a horizontal to really tie in that coronal plane activation and get a big boost of brain activation into people's brains because they need it now more than ever. Thank you guys for playing along, and we'll see you soon. Hopefully our next conference is in person so we can kind of put away the digital stuff.